Hello everyone, welcome back. I am Divavardhan Singh and today we are talking about one of the most beautiful and a very beginner friendly algorithm in machine learning, that is decision tree. Okay, before I throw any maths at you, let me just ask you a very simple question, that have you ever played the game of 20 questions where someone asks you yes or no questions? Okay, if you have, then you already get the theorem. It is exactly how a decision tree works. It learns through a series of yes and no questions that split your data into smaller and smaller group until each group is as pure as possible, meaning that mostly one class and one answer. Okay, so why should you care about it? Decision tree are one of the most readable machine learning algorithms. You can literally look at a training tree and read it like a flowchart. If a age is greater than 30 and income is less than 50k, then predict no. That's it. No black box in it, no mystery. You can explain it to anyone very easily. Okay, they also do not have any of the feature scaling unless and unlike the linear regression or the SVM. You don't need to normalize your data. They work with both the numerical and the categorical data. Okay, third point is that they capture the non-linear pattern without any fancy feature engineering also. And here one of the here once a big thing, that the random forest and the gradient boosting, XGBoost, light GBM, the algorithm which dominate are also some ensembles of the decision tree only. Okay, one thing to note down is that the decision trees are non-parametric. They make zero assumptions about the shape of your data. Okay, so they are super flexible, but that flexibility comes at a cost of overfitting also, that we're going to see in the section 3. Okay, moving forward, we have some of the anatomy of a tree related. At the very top is the root node. The first question, always the most informative feature. Below there are the internal nodes. The middle questions each split data on some condition, like is this value less than or equal to some threshold. The lines connecting nodes are called as branches. They carry your left or right based on the true or false. At the bottom are the leaf nodes, the terminal nodes. Okay, these give you the final answer for the classification. That's a class label. For a regression, that's a number. Okay, and depth is just the length of the longest path from the root to the leaf. A tree of depth 2 can have at most 4 leaves region. Okay, making prediction is dead simple. First of all, start at a root, evaluate the condition at each node, follow the true false branch, then keep going until you hit a leaf. Fifth, output wherever the leaf says. Okay, and the time complexity at the inference, so it's just big O of D, where D is the depth. Okay, so now let's move forward towards the section 2, the maths about the impurity, information game, and the cart algorithm. One of the most important question is that how the decision tree decides which question to ask at which step. Okay, this is where the maths come here, and I promise that it's not as scary as it look. The first key idea is of impurity. At every split, we want the child node to be as pure as possible, ideally containing only one classes. So for that, we have some of the functions, or we can say some of the entropy like gains which we can use. So first one, which is the entropy. Here entropy comes from the information theory. The formula is as given as hs equals to minus summation of pk into log 2 pk, where pk is the fraction of the sample belonging to class k. Think of entropy as measured as the disorder or the uncertainty in a node. If your node has 100% one class pure, then the entropy is 0, no uncertainty. If your node is a perfect 50,50 split between two classes, then the maximum confusion, entropy hits 1 bit. Okay, let's take a quick example. 5 yes, 5 no, so that's 0.5 and 0.5 h. So the entropy will be equal to, by calculating on the formula, we'll get 1. That is the maximum disorder. Okay, entropy is used by the ID3 and the C4.5 algorithms. Second one, we get the Gini impurity. The formula is GS equals to 1 minus summation of all square of pk. For a binary problem, this simplifies to 2p 1 minus into 1 minus p, with the maximum of 0.5 at 50-50% split. Same example taking, we get the g value as 0.5. Gini is faster to compute because there is no logarithmic involved. It is default in the scikit-learn and is used by the cart algorithm. In practical, this is very important for the exam also, as Gini and Entropy are nearly same identical trees, but Gini just gives slightly faster as compared to Entropy. Third thing is the most important, which is E of S equals to 1 minus max of pk. That is the misclassification error. This one is really used for actual growing tree. It is not mathematically concave enough to reward splits that create one very pure child. So just know it exists, but card doesn't use it for splitting. Okay. Now, how do we use the impurity to choose the best split? That we called as the information gain. Information gain is being calculated using this formula. So let me tell you how this formula works. You take the entropy of the parent node and subtract the weight average entropy of the child nodes after the split, and that's where you are left with the information gain. The higher the information gain, the better is the split. We always pick the split that maximize the information gain. Okay, so let me walk through a quick example. For example, we have 10 samples, 6 yes, 4 no's. Okay, we test a binary feature A. Parent entropy h of x equals to minus 6 by 10 into log 2 6 by 10 minus 4 by 10 into log 2 of 4 by 10, and it comes out to be 0.971. Okay, now after the split, left child has 5 samples, all yes, entropy equals to 0. Right child has 5 samples, 1 yes, 4 no's. On calculating the entropy, we get it as 0.722. Now we calculate the IG for both. We get the IG for the first case and the second case, and taking the average of it and subtracting it from the parents one, we get the 0.610 bit. That's a big gain, and the split is very useful. One more important thing is that information gain is biased towards high cardinality feature. A feature like user ID, which is unique for every sample, would trivially achieve maximum IG by creating one leaf per sample. To fix this, the C4.5 algorithm uses the gain ratio, which divide the IG by the split information of the feature, penalizing the features that can create too many branches. Okay, so now let's move forward. We'll know how we can actually build a cart algorithm. Okay, so the process is very recursive and easy to understand. First, look at the current sample set of sample. Secondly, try every possible feature and every possible threshold. Third, compute the Gini reduction for each candidate split. Fourth, pick the feature threshold combining that given the maximum Gini reduction. Fifth step is split the data into left and right subset. Sixth one is recursive this on each of the subset. On continuing this feature, cart tries all the midpoints between consecutive sort values as the candidate threshold. The cost of it comes out to be big O of m into log of m per feature due to sorting. Okay, so the total cost of the building the tree is big O of n cross p cross m log of m, totally flexible enough for moderate sized database. Okay, the tree stop going once a node become a leaf. Okay, the maximum depth is being reached there. Yep. So there are some more points, but that are not so important. Moving forward, we have another important topic, that is the regression tree. So basically, regression tree works the same way, but instead of the Gini or the entropy, we minimize the MSE, mean square error. Okay, as you can see, the formula showcase the change in the MSE of V, that at each node, instead of outputting a class label, we output the mean of all the target values in the leaf. The prediction is piecewise constant, like a step function over the feature space. There is an important note that decision tree do not extrapolate for input outside the range of the training data. The tree just return the leaf mean, the most extreme value it can see. Okay, keep this in mind. Now moving forward towards the section 3, which contain overfitting, pruning and important features and the key takeaway. Alright, so when we build the tree, now we have to talk about one of the most biggest problem, that is the overfitting. A fully grown tree will memorize the training data. If you let it grow until every leaf is pure, it will get zero training error, but it will completely fall apart on a new data. So we need to control the complexity. For that, we'll do pruning. There are two types of pruning which we can do. First one is the pre-pruning, also called as early stop. This means we stop the tree from going too much in the first pace using hyperparameters like the max depth, minimum sample split, minimum sample leaf, minimum impurity decrease. These all we can use in the case of pre-pruning. Pre-pruning is fast. The downside is it is going is greedy, so you might stop it earlier. Okay, now moving towards the second, that is the post-pruning, cost complexity pruning. Here what we do is that you grow the tree full to the end and then trim it back. Okay, the critication for this is as given, where r of t is the training error, mod of t is the number of leaves, and alpha is your complexity penalty. When alpha equals to 0, you will get a fully unpruned tree. As alpha increase, the tree get pruned more and more, and you can choose the alpha parameter according to the cross validation. So for choosing the alpha, we'll be understanding this all in the hyperparameter optimization, which we'll be gonna talk in future lectures. Now let's talk about one more thing, that's the bias variance trade-off, which is fundamental. A very shallow tree has a high bias, it's too simple, it's underfitting, so it misses the pattern of the data. A very deep tree has a high variation, so it memorizes the training data and it overfit. The sweet spot is somewhere in the middle, a tree depth enough to capture the real pattern but prune enough to get it generalized well. Okay, now moving forward, we have one of the most important thing, that decision tree give you is given you for a free of without any feature importance or a feature engineering. You don't need to do any of the feature scaling or feature engineering while using a decision tree. Yeah, so f of j, there's a formula of f of I given j. Okay, these scores are normalized so that all the sum of these scores goes up to 1. This is the feature importance score. A higher score means that the feature is more informative, the tree is more reliable to make a decision. This is used for the feature selection when you train a tree and look at the importance and drop the features near to 0. Okay, a warning here is that feature importance for a single tree is unstable, so change your data slightly, and that's why we don't majorly use this all in the case of decision tree. We'll be using it in the random forest more. Yeah, so about the parameters we have already discussed. These are some of the parameters for the hyperparameter tuning or the optimization that we'll be seeing. Yep, now let me go towards the assumption and the limitation. So what are the tree assumption? Axial alignment split are sufficient for it. Secondly, training data is representative, and third one is that no specific distribution required for it. Okay, remember we have already read about it, that it's non-parametric. Some of the limitations are that it has a high variance, diagonal boundaries, then it's greedy as it goes to down to the depth it can go. Third one is the cardinality bias. Yep, so we got some of the key takeaways from the complete lectures, and here how we have wrap up with the decision tree. We'll be covering that how we can solve more questions over the cart algorithm and other pruning like the alpha beta pruning and other in the upcoming lectures. Thank you.